Hi guys, welcome back. So what we've got here is we've got part two. Um, and in part two, what we're going to be doing is looking at the interactions between strong and weak. Now, for reasons that we're going to get into much later in this unit, there are a variety of different places that you can mix a strong and a weak together. When we did our last unit, when it was a strong and a strong situation, it was relatively easy because we knew we would be left with a certain amount of either the strong acid or the strong base, and that would be easy for us to put it through the pH square. As we're going to see in these particular problems, when you do strong and weak, things aren't necessarily going to be as straightforward, and there are a variety of different places when you go to do the math that this kind of a system can end up. It can end up when they're equal. That's what we're going to look at first. It can end up when they are halfway. It can end up when they are before halfway, after halfway, all sorts of different places. But for reasons that we don't need to get into right now, we are just going to focus on what's called the equivalence point. And the equivalence point is just what we've talked about before when you're talking about the strong situation. It's just when the acid and the base are equal, when they are the same. Now, you might say to yourself, every time the acid and the base were the same in the last section, it was easy. It was a pH of 7. Well, sure, that makes sense, because when you have a strong acid and a strong base that react fully to 100%, if you have equal amounts of them, they will completely neutralize each other, and you will end up with a pH of 7. But think of this. Let's say that you have a strong acid, but a weak base, and they're the same. They're at the equivalence point. Well, who should win? Well, if the acid is strong and the base is weak, then the acid should win, and you should actually have a slightly acidic pH because you have a strong acid that is overtaking a weak base. Similarly, if you have a strong base that is at the equivalence point with a weak acid, then the strong base is going to be, again, for lack of anything better, stronger than the weak acid, and you should end up with a basic pH. And what we're going to discover is that there is a long, really difficult way of going about doing these things, and then there are some easy shortcuts for us to get through. But let's take a look at the full thing for the first time and see if we can't figure out why we're going to be able to make a shortcut eventually. So enough talking. Let's take a look at this, and let's walk through this process here if we could. So first things first, can you notice that what we are doing here is we are mixing a weak acid that's here with a strong base. You see that? A weak acid with a strong base. How do I know that this is a weak acid? Well, a couple ways. Number one, acetic acid is not one of the ones that I told you to memorize that was strong. And number two, I told you that it had a Ka value. So as soon as you find out that it has a Ka value, you should know, okay, immediately this is a weak acid. And what we are doing is we are mixing that with a strong base over here. And again, how do we know that this over here is a strong base? Well, it's one of the ones that I told you to memorize was a strong base, sodium hydroxide. Now, you should be able to look at this. I arranged this first problem, and just right off the bat, recognize that this is going to be at the equivalence point. We're going to have equal amounts of acid and base. And you should be able to know that because I kept it really simple for you. 100 milliliters and 100 milliliters, so they have the same volume. 0.2 molarity and 0.2 molarity, so they have the same concentration. So these guys are going to be at the equivalence point. But before we get into any of this, let's take a moment, if we could, and do what's going to happen. Again, when you mix two solutions together, we are going to dilutify them. So my acid here is going to be, again, a weak acid. And so it's going to be 100/200ths of 0.2 molarity, or obviously it's going to be 0.1 molarity of my weak acid. My strong base is going to be 100/200ths, just like we have done now a whole bunch of times. 100 and 100 go together to make your 200. So it's going to be 100/200ths of, again, a 0.2 molarity. So you're going to have 0.1 molarity of your strong base, which is the OH negative, and this is your HC2H3O2. Please note that I gave it to you in this form, NaOH, but knowing that it is strong, it's going to break completely into the Na positive and the OH negative. And if you haven't figured out yet that the sodium ion is a spectator ion in all of these things, then I really don't know what you've been listening to all year. So we're going to keep this real simple, and we're going to go with just the OH that's there. Now, let's examine what it is that they've given you and presented to you, and take a look at the problem as presented to you and see if we want to do it that way. So the problem as presented to you is these two guys mixed together. So we're going to have HC2H3O2 plus OH negative. Now, right off the bat, you should recognize that we have not done any problems in this format. How do we know? Because in every single one of the formats that we have looked at, water has been on the left-hand side. And if we take this weak acid and this strong base and put them together, then water is actually going to end up over here. We're going to end up as H2O, and then we're going to end up as C2H3O2 negative over here. So this is not the format that we are used to seeing here, not at all. So if we tried to do math with this equation, we wouldn't be able to. What you're going to want to do is you're going to say to yourself, oh, okay, well, I'm just going to use this as 1 times 10 to the negative fifth because that was the Ka that they gave me. Stop, time out. This is not Ka. Remember, Ka is the weak acid plus water. This is not the weak acid plus water. This is the weak acid plus OH negative. So there's all sorts of things wrong with this right off the start. So this 1 times 10 to the, or 1.8 times 10 to the negative does not work for this equation. So we don't have a number actually for this equation. Now, we can get it if we're so interested. What we can do is we can do Ka, which would be HC2H3O2 plus water, comes over here to form H3O positive and C2H3O2 negative. That would be a 1.8 times 10 to the negative fifth because it is in the proper Ka format. But please note that this equation that we've written here and this equation that we've written here, while similar to each other, are not the same. So I want to do math with this equation here, and I don't have a number for it. Now, technically speaking, we can get it. We just have to include the opposite of Kw. How do we do that? Well, check this out. H3O positive plus OH negative is going to come over here to make H2O. Remember the Kw that we talked about at the very beginning of this unit? I'm sure Mr. Comerford talked about it. Well, that had a value of 1 times 10 to the negative 14th, right? But remember, that's the autoionization of water, and what we have done is we have flipified it. So in doing so, this has actually become 1 times 10 to the positive 14th here. Now, why did we have to flipify it? Well, check it out. If we now do a little equilibrium Hess's law situation, the guy on the left and the guy on the right here cancel each other out. One of my waters cancels out here with one of my waters here. And now check out what I have. I've got this and this, which work out together. I've got this and this, which work out together. And I've got this and this, which work out together. And then I've got this and this, which work out together. So by combining this equation here with this equation here, I have actually created my third equation up here that I wanted to begin with, right? Now that means that the K value for this equation up here is going to be the product of these two values, because remember in equilibrium when you add substances together you multiply their K values, and so you're going to get 1.8 times 10 to the negative fifth times 1 times 10 to the 14th, and so you're going to end up with what is it, 1.8 times 10 to the positive ninth. Now, before you get all excited that you now have a number that you could work with, all of the shortcuts and everything that we taught you before are now no longer valid. Why? Well, I'm going to erase all of this because all of this was just in an effort to get that purple number. So even if I were to go here and do an I, a C, and an E, this would be a 0.1, and this would be a 0.1, and this would be who cares, and this would be 0 that's there. Every other time that we have done this, we have done a minus x, and a plus x to get x, and then 0.1 minus x, and 0.1 minus x. In this particular format, you would be talking about 1.8 times 10 to the 9th is going to be equal to x over 0.1 minus x quantity squared. And no, you could not ignore this minus x here and here. We have to keep them. Why? Because when we can ignore them in the early stages of things when our k value is small, but our k value here is huge. So now we've got some really awful, ugly quadratic thing that's going on here. We're not able to do any of our tricks, and everything about this problem is just wrong from the start. Everything about it. The format is wrong. The numbers are wrong. All the tricks that we learned before are wrong. Everything about this guy is just wrong from the start. And the problem is that there is a slick and elegant way that we could solve this problem, but it's going to take a little bit of flimflammery. It's going to take a little bit of a thinking outside of the box kind of a situation, because everything that we are being presented with here is wrong, and I don't want to do it this way. So, how are we going to get out of this? Well, the easiest way to get out of this is to recognize that water is a product. And if water is a product, that means your k value is going to be big. And if your k value is going to be big, like we just saw, that purple number that was here, that 1.8 times 10 to the 9th, if your k value is big, well, that means that this guy here is going to go almost all the way over, but just not completely all the way over, which, again, we know from equilibrium. And speaking of equilibrium, let's not forget about our most important asset here, this guy here. This guy here says that this reaction goes left to right, but it also goes right to left. So, if instead of being presented with this equation that we don't like at all and try to force ourselves to do this equation from left to right, what if we did a little jiu-jitsu here and used this equation's energy against it, and instead of going from left to right, let's take the equation all the way over and then flipify it and start from right to left. We said that this equation is going to be big. So, if this equation is going to be big, just humor me, and let's assume that it's going to go all the way. So this is minus 0.1 and minus 0.1 and plus 0.1, right? To be left with none and 0.1. Now, we know this is not right because we can't have zeros that are here like so. But if we did that, now check it out. What I've got here is I've got 0.1, and I've got 0.1 only of this substance right here. Now let's take this equilibrium stuff that we know is not quite right because there are these zeros that are here, and let's, instead of looking at this from a left to right situation, look at it from a right to left situation. Or in other words, let's take everything that we see here and we're going to flip it and we're going to do it backwards. So check it out. This is going to be C2H3O2 negative plus a water is going to come over here, and it's going to form OH negative, and then HC2H3O2. I've got an I, I've got a C, and I've got an E, and I don't care about this. This is starting to look a little bit better, right? Because at least water is on the left-hand side, the reactant side, which is what we want. And knowing that this here was where it ended up when we forced it all the way over to the right, that's going to be now my new starting position that's here. So it's 0.1, and then I'm going to start with 0 and 0 here. Now, this would be great, except I need a k value for this, and I don't have one. Or do I? Bum, bum, bum. What format is this equation here now in? I have a substance here plus water, and it's going to go to OH negative, and then this guy over here. Oh, wait. This is Kb. This is the Kb of the acetate ion. Except that we weren't given Kb of the acetate ion, except we were. It was just given to us in stealth format. What do I mean by that? Remember that they gave you Ka of the acid version of this guy here. And remember that if you're talking about Ka times Kb is equal to 1 times 10 to the negative 14th, and you know what Ka is, then you automatically know what Kb is for the conjugate base. So this is going to be 1.8 times 10 to the negative 5th times Kb is equal to 1 times 10 to the negative 14th that's here, right? That's Kb. And so, solving using a little mathification here, we have 1 times 10 to the negative 14th divided by 1.8 times 10 to the negative 5th. We end up with 5.56 times 10 to the negative 10th. So Kb is 556 times 10 to the negative 10th. So in spite of the fact that they didn't give you Kb, they actually did kind of give you Kb because they gave you Ka. And if you know Ka, you know Kb. If you know Kb, you know Ka. So what I have here now is I have 556 times 10 to the negative 10th. Well, now all of a sudden, this becomes a trivial problem. Check it out. This is going to go down by some amount x, up by some amount x, up by some amount x, and it's going to be 0.1 minus x. It's down here. If you want to, you can use the common ion effect and just completely ignore this x that's here. Why? Because the Kb is an extremely small number. And now, all of a sudden, this is starting to look very, very familiar. 556 times 10 to the negative 10th is going to be equal to x squared over 0.1. So then x is going to be equal to 7.45 times 10 to the negative 1, 2, 3, 4, 5, 6th. 745 times 10 to the negative 6th. Please note that x that we've got here is what the OH is. So in reality, what I have just solved for is I have just solved for the amount of OH. And if I know any one of my four corners of my pH square, H positive, OH negative, pH, and POH, if I know any one of my four corners, I know all four corners. So this is 745 times 10 to the negative 6 if I've done my math right. Which means that if I then take the log of that value, I end up with a POH of about 5.13, and then therefore a pH of about 8.87. So that was a way easier, and I know it might not seem it right now, but that's actually a way easier process to go through than to do what it is that they presented you with. So if you are presented with a strong, weak system and it's going to be at the equivalence point, then what you are going to do is you're going to follow a series of steps. Step one, you are going to first dilute the system, assuming it needs it. Step two, because you are being presented with a weak, strong situation, you are going to take it all the way over those diluted systems, all the way over to the right-hand side, and then flip it so that it turns into the conjugate idea of it. So if it's a strong base, weak acid, you're going to end up with a Kb. If it's a strong acid, weak base, you're going to end up with a Ka, as we'll see in our next example here. And now once you turn it backwards into its conjugate system, it just turns into a typical problem that we were used to seeing from part one. So the whole idea of this is that we don't want to reinvent the wheel here. What we want to do is we want to take a system that is complicated, weird, and difficult, and that we don't have the tools to use easily, and modify it slightly so that we can do it in a way that we are used to seeing. Because if I had just said, what is the pH of a 0.1 molar solution of this weak base, and had given you this number, you should have been able to solve this no problem. but I didn't give it to you that way. I gave it to you in the way that it is a strong, weak system at the equivalence point, and a strong, weak system at the equivalence point is going to result in exactly this kind of thing. So what we're now going to do is look at some more examples of this, but this time we're going to go straight to the easy way of doing it rather than trying to figure out the hard way of doing it first.